Hi, welcome to CS61A Fall 2015 video walkthrough for the final. My name is Raymond, and both James and Michael will also be going through some questions.
Okay, so this is question one. This is a what would Python print. It's really nice with these object-oriented type questions to draw a little diagram. So I'm going to draw the Adele class. We have a class variable times, which points to 1,000. Then we have an init method. It points to an init method and an str method. I'm going to do the same thing for hello, but it's important to note that I'm going to draw an arrow that basically I'm going to say it inherits from the Adele class. So hello only has a next method. Remember, we don't actually have to have a init method because the init method's inherited. That's the whole point of inheritance. Okay, now we have a never equals iter scheme to be home. So remember that strings are iterable. What does that mean? Well, an iterable is an object that we can iterate through. By definition, it means that its iter method return value is a iterator. So although we're not doing it in this problem, it's important to note that we can say for x in iterable, like we can loop through a string, for example. What this does under the hood is it calls the iter method, then it calls the next method, then it calls until it hits a stop iteration. So what our program is going to be sort of doing is breaking it apart. We're calling the iter method, and then we're going to be calling the next method instead of doing it in a for loop. But you need to know that you can do it in a for loop as well. So let's draw that maybe in our sort of global frame, because we need to keep track of our never. So never is going to be pointing to this string scheme to be home. Actually, it's I'm going to put in parentheses it's a iterator because we called iter, and that's important as well. Okay, so then we have an any function that points to a function any. And now we have a outside. So outside is going to be an instance of the hello class. So how I'm going to do that is I'm going to draw a little box. This is going to be outside. It's going to point to our hello class. This is going to say instance. And so now we run through the constructor. So the constructor says self.call equals u. Well, u is a function call, any parentheses any. So I'm going to draw that here. Any parentheses any. But the interesting thing about Python is if we are evaluating a function that has yield statements in it, what's going to happen is calling any is just going to return a generator. This is really tricky because normally when we have a function call, we're going to be, calling our function, then going line by line. But we don't do that yet because our function is a generator object. So the only way that we can actually go through our code is by calling next on any. If we were to call this somewhere in our code, then we'd be able to go line by line. Does that make sense? Because we have a yield statement, this is just going to return a generator object. So we go to our outside class. We say self.call is now going to point to, okay, I guess I will draw a little arrow. It's going to point to this generator object, any. So this is actually the more parameter, but we're passing the any function in. Okay, so now we can walk through our code. So next never. Let's look at our global frame. We have a never. We have a scheme to be home that's actually an iterator. So we can call the next method. So what's the next method going to do? It's actually going to return the value, sort of the first value in the string, and then move on to the C. So now our iterator is going to be pointing at the C, but it'll actually return RS. Does that make sense? Because, if we have an iterator, we can call next, and it'll get the first value and then move on to the second value and keep going. Sort of like a list, we can call next and get the first value. All right, so next outside. Okay, we're going to look at a next method. Is there a next method in our, remember, underscore next is a magic method. So we can call it like so. So we look into our hello class. There is a next method. So then we go into our next method, it's going to be calling next of self.call. Let's look at our outside function instance. Look at self.call. Remember, self.call points to this generator object. So now, just like I was talking before, we actually did call next on, in our case, self.call, which pointed to any. So now we actually walk through the code here. I'm going to erase this. We're going to be walking through the code here. Does that make sense? Because we called next on self.call. Actually, we called next that called the hello next that called the next of self.call, which is a generator object. So now we actually walk through. So let's look at our code. It says next and then increments never. So we look for never. Never is in our global frame. We increment it. But remember, we don't print it out because this is inside of a function and we aren't saying print next never. But all we're doing now is going to be incrementing now to the h. But we're going to print outside. So we look for our outside. There is no outside. There is an outside in our global frame. I forgot to write that. Outside actually points to this instance right here. But now we say print outside. So remember that print, I'll draw it here, or I'll write it here. Print calls the double underscore str. So we're going to print outside, which is an instance of our hello class. We look at our hello class. There is no str method. We look at our inheritance. There is an str method. So we go here, return self.times. So all this is going to do is print self.times. Remember, our str method has to have a return statement. So it's going to print self.times, which is 1,000. And it's going to come out like 1,000 because remember, saying something like print, hi in strings gets rid of the strings. And so just that's what happened here. Okay, now we can actually move on to our yield statement. So our yield statement is going to now yield next never. What does yield mean? Well, yield is like a returning, except it knows its place. So whenever we call, like when we call next again on our any method, we actually will start back at the yield value. But so we return this value next to never. Let's go to our never. Never is this string. We call next, so it'll actually return the h and move on. So it'll return our h. But it's important now that I'm going to put a star there because we're yielding this, which means the next time we call next, it'll resume its position there. All right, so that's what happened right here. Next outside. So we resume our position exactly where we left off because outside, this is the exact same reasoning. What happened here, we called the next of the hello, next of the generator. So we resume, we print next never. So let's look at our never. Next is the e, we cross it out, we print it. Remember, you're saying print hi, you take out the quotes. So then we have, actually I'm gonna need a little bit more room. Then we have the next value, yield more. So more is any. Any is again a generator object, as we saw before. So this is going to make another any here. We'll call this 2. This is our second any. I'm going to put in parentheses. This is actually our more. So we yield this. This returns a generator. Same reasoning before, because any is a function call to this function, and this function has a yield statement, so we don't actually go inside until we call it next. So we can actually now go back to here. We know next outside is going to be a generator because this is yielded right here. So now we can call next of our generator object, and this next method will go to restart. It's sort of like another instance of a generator object with this any method. So we're actually going to be here. I'll draw the arrows on the left side. So this is our second generator. We call next never. We go to never. We cross out the m. Cross it out. Remember, we don't print it or anything. And then we print outside. So we look here. There is an outside. Call the str method. We print 1,000. And then we yield. Now we're on this line right here. I'll put a star. We yield next never. We go to never. We cross this out. We yield it. So we get character E. All right, now let's look at list never and then list splicing. So, or list splicing. So list never. Never is this never right here. Note that it doesn't restart to scheme TB home because it's an iterator object, and we actually were going through it. So sort of like how an iterator, like the analogy is like a bookmark. We've gone through our book, and then we're now going to convert the rest of the book into a list. So we're going to convert the rest of the book, just this part, to a list. So that is going to look like 2 B H O M E. All different indexes in our list. And remember that we can convert strings to lists, and that'll actually turn each letter of our string as a list. And that's something to remember as well. So we look at our list splicing, :3. Remember, this is our start index, and this is our end index, and this is inclusive, and this is exclusive. So inclusive, we start at 0, so we actually get 0, 1, 2, and then we don't include the 3. So our final output is going to be 2 B H. Does that make sense? We converted the rest of our never to a list and did that. Okay, so let's go back now to next outside. So this call is very similar to this call. This next outside, remember we were looking at this right-hand side where our star was. Remember, our star is now at our more, which is what was the last time we called next outside. So we actually call it, we continue, but notice how there's no more lines afterwards. Remember, this next outside is actually referencing this generator object right here, not this one, because this one is only visible to this local call. So we call this generator object. It has nothing left, so that'll actually raise a stop iteration. I should have reviewed what a generator is. So remember, a generator is a special type of iterator. So it does, when it runs out of things to yield, it'll raise a stop iteration. And so this will actually raise an exception. Oh, why is it exception? Okay, yeah.
All right, so we're going to do this environment diagram Endor. And from the looks of it, they already defined temp for us. So in the global frame, what we have to define is Sith and Jedi. So going down, it looks like Sith is going to be some empty list. So we can just write this as some list here right now. And then Jedi has one element in its list. So, we'll say list with 3. They define temp for us, and we know that we don't actually execute the body of this function until we call it. And so we call it in here, temp with Sith. So we're going to open up a new frame, which they've defined as temp, and the parent is global. And they're going to set power to Sith. So we have some power. And this is bound to what Sith is pointing to. And we know that Sith is pointing to this empty list. So let's just draw a pointer to this empty list. So now we're executing the body of temp, and it looks like force is bound to some lambda function. So the next thing we want to do is write force, and let's point it to some lambda. We'll say this is func lambda 1, and it takes no arguments, and the parent is where we defined it, so it's going to be F1. Temp is then going to be bound to force. So we have temp pointing to what force is pointing to, which is this func lambda. Okay, and now we're going to define balance within here. And for balance, we're just going to say func balance. This takes in some parameter force, and the parent is F1 because we defined it in the F1 frame. And then we're going to return balance of 4. Okay, so we're going to call balance here, and we're going to copy this parent over, which is F1. And now we're going to execute balance of 4. So force is going to be bound to 4. And we notice that, okay, here's a non-local power. And what does that mean? Essentially, we're allowed to edit what power is in our parent frame. So we look in F1 and we see that we have a parameter power. And now we're able to change that in the F1 frame instead of the F2 frame. So it says a power.append force. Now, from here, it looks like power is an empty list, and we want to append force to it. And so we're going to find force by looking it up in our current frame, which is 4, and then we're going to append it in the list in our F1 frame. So we have 0, and we have 4. And then after that, it says if force is less than 2, we're going to return tempt. We look at force in our F2 frame, and it's currently 4. So we're going to just ignore that if statement. And now it says power equals Jedi. So power, remember, we non-localed it. And so power in the F1 frame is going to be bound to Jedi in the global frame. So we can erase this. Oops. And point it to Jedi. Okay. The next thing we want to do is call return balance of 1. And then we're going to evaluate this portion first. So let's see. Balance, when we call it, we have to open up a new frame. And the parent for this is going to be F1. We know that force is going to be bound to 1 in this case because you pass in a 1 for the argument. And we're going to non-local power again. So non-local power means we can edit the power parameter, the power variable in our F1. And so it says we're going to append force to it. And power currently points to this Jedi list. And so we're going to append force, which is 1. So we appended that to this current list. And then we're going to say if force is less than 2, we're going to return tempt. So in this case, force is less than 2. And so our return value is going to be pointing to what tempt is pointing to. And we know that tempt points to this func lambda. Okay. So now that we know that this portion evaluates to some lambda, we're going to call it with our empty parentheses. We know that this lambda is the one we're going to call. So let's open up a new frame, lambda, and we'll define this parent as F1. And it looks like it returns some list. And in order to know what this list takes in, we have to evaluate the operands. And so we're going to point this to some list. And we know it's going to be 2 elements, but we don't know what's in them yet. So it's going to be the length of power, which is, if you see here, power is currently a 2-element list. And then it's going to be force. So we're going to look in the F1 frame for force, and it's going to be this func lambda. So we're going to make a pointer to this func. And that's the bulk of it. So when we return out of here, we're going to point this to this list. And then we're going to return out of tempt. And we know that this tempt frame has no return. So essentially, its return value is going to be none. All right, so this problem is essentially testing your knowledge of Python list mutations using special functions such as append, extend, and pop. So just walking through some quick examples. Append essentially takes an object and adds it to the end of your list. So if we define x to be 1, 2, 3, and y to be a list 4, 5, if we x.append y, we're going to add y to the end of our list. So x is going to be 1, 2, 3, and the full list 4, 5 as one whole element added at the end of your x list. The difference between append and extend is that extend is actually going to iterate through your iterable. So what that means is if we x dot extend y, it's going to add 1, 2, 3, but then it's going to go through each element of y and add that to the end of x. So we see in y we have 4 and 5. It's going to unpack that and add it to your x list. And so that's the difference between append and extend. And as you can see, one actually just puts the entire object at the end of your list, while the other one unpacks it, to say. And we have another function, pop. And what this does is, okay, so if we have a list, x is 1, 2, 3, and we pop x, then that's essentially going to take off the last element of your list if you don't specify any arguments and return that value. So x can be 1, 2, but the return value is going to be 3. Okay. Similarly, these return values are going to be none because they mutate a list. Okay. So using this information, we can now approach these problems. First off, it looks like we want to define some S, and it's a list that has 2 as the first element and some func lambda as its second argument. And it's convenient because they already defined it for us. The next thing we want to do is we want to do s.append, the first element of S, and we're going to call that. So we're going to index into our S, which is this func lambda, and we're going to call that with no arguments, okay? So we're going to use this lambda and create a copy of our current list. So we're going to append a copy of this list. So our current list consisted of 2 and a pointer to this func. Okay, so this is the second element, and that's what append is. If we extend it by indexing into the first element and calling this lambda, we're going to create a list of our current elements in here. So we can think of it as we're creating a list of what we have now, which is 2, a pointer to some func, right? And another pointer to some list, just for clarity. So we're going to iterate through each object in this list and then append it at the end of this S list. So our third element we can see is going to be a 2. Our fourth element will be this pointer to this function, and our fifth element is going to be a pointer to this list. Okay, so that's it for that problem. All right, so doing part 2, we see that it's a similar structure to part 1. We're essentially going to initialize some list, and we see that this one has a 2 as its first element and a lambda function as a second, which is also conveniently defined for us. So the first thing we do is append S of the 1 comma to the end. So what that means is a list splice, and by list splicing, you're creating a new list. So that's an important thing to note. And list splicing this current list, we're just going to have this func because that's everything from index 1 to the end. So let's draw it out here. We have in our list, it's going to be some pointer to a func. But then outside of this list is another list. So the first thing we're going to do is we know that we're going to append a list to this. Inside of this list is another list, as if that wasn't confusing enough. Okay, and inside this inner list is going to be the pointer to the function. Okay, so that's append. And for extend, what we want to do is do the same thing, where we splice the list from 1 onward. So now we have 2 elements in our splice, and it looks like it's going to be surrounded by another outer list. So the elements in this outer list are going to be this pointer to a function and a pointer to another list. Okay. And now when we extend something, we know that we have to iterate through all the elements in our list. And since we're extending it, we're going to iterate through the elements in our outer list, not the inner one. So that's an important thing to note. So because we only have one element in our outer list, we're just going to extend it by this. So we know that we're extending our list S by one element, which is another list. Inside of this list, however, there are two pointers. One is to the function, and the other one is to this list. And the tricky thing about this problem is just noticing that there's a list within a list, and that list comprehensions actually create another list. All right, so moving on to part 3. This problem is a little tricky, and so I allocated some extra space on the side for it. So similar to the problems we did before, we're going to initialize S. The first element of S is going to be a 2. And the second element, index 1, is going to be some func lambda. And the parent's global. Okay. So we're going to append this other lambda function at the end. So attaching onto S, we're going to have another func lambda. Let's call this lambda 2 now. And the parent here is going to be global. Okay. So we're extending by S of 2, and we're calling that. So in order to not lose track of where we are, let's just draw this out step by step on our scratch paper. So we want the return value of S of 2, so we know what to extend it by. And so we don't know what this is yet. And so we'll find that out by calling this lambda function over here. So when we call this lambda function, we know that we're going to return some s.append, but we don't know what the value we're going to append is yet until we pop it. So we're going to append it by some value. So in order to solve this problem, we have to evaluate it argument first. And so breaking it down, we're going to go into the innermost arguments. So we're going to s.pop our last element off list S. And so we're going to essentially take this element off, but we're going to call it because pop returns that value. And so we return this lambda function, and we're going to call it again. So calling lambda 2, which is the same function that we were just in, we're going to open up essentially like a new frame, if you want to think about it like that. And this return value is unknown right now, right? We have to evaluate the arguments inside s.append and s.pop. So similar to what we just did, we're going to s.pop again, and now we get this function. So evaluating this function, we're going to list our current s. And currently, our s is just one list. It's just a one-element list with 2 inside. And so we're going to s.append this list 2. Okay, so let's draw out a new list here. We know the first element is going to be 2, and the second one is going to be some list with 2 in it. Right? Okay. So the return value of appending after we did that is going to be none. And so this lambda that we were just in is gonna have a return value of none inside of a list because it's surrounded by these brackets. Okay, so now that we have this information, we know what to append here. We're going to append a list of none. So the next element that we're adding onto our list S is gonna be a list containing just none. So we have none. Okay. And we know that s.append none returns none itself. So we know that this is going to correspond to the return value of this whole thing, which is just a list of none. So when we extend it, remember that we're going to go through each element instead of our iterable. And in this case, the index of 2 on S, this is going to be our iterable. And it's just this list none. And extending it, we're going to add each element to the end. So we only have one element. And so this third element is just going to be none.
All right, so for question 3a, we're looking at big path, which returns the number of paths in a tree whose sum is at least n. So a path is a list of adjacent nodes, node values, such that we're going to start from some root value and end at some leaf. So if we look at this example tree here, a path could be 1 to 2, 1, 3, and 4, and then 1, 3, and 5. Now, in big path, we want the paths such that the tree values on those paths sum together to be greater than or equal to n. So the simplest tree that we can think of is, let's say, a tree with just a leaf. So in this case, 2 itself is a path, and since it's a leaf, the only value on this path is just t.label, t.label. And so in order for this to be at least n, then t.label must be greater than or equal to n. So here we do if t is as leaf, and for a base case, and for a tree, we're going to make sure that t.label is greater than or equal to n. We're going to pass this into a function 1, which returns 1 if the Boolean is true. If not, it's going to be 0. So in this case, if it's true, then we're going to return 1, which is the number of paths that we have that satisfy the constraint. So let's look at the recursive case. Remember, trees are made up of a root value and a list of subtrees. So since these are all trees, we can make the recursive call to each one of them. But we want to think about what's the n value we want to pass down. So in this case, if we go left 1 to 2, then our current path has already looked at 1. So if we already looked at 1, then 2 must be greater than or equal to n minus 1 in order for it to work. So if we have some path from this subtree onwards that is greater than or equal to n minus 1, then it must mean that up here, the path from 1 and 2 or anything that's below it has to be greater than or equal to n. So we're going to pass n minus 1 down here, and also n minus 1 down here. So again, looking at 3, we get n minus 1 passed in, and our possible paths is 1, 3, 4, or 1, 3, and 5. So having looked at 1 already, we're looking at 3. So the value we're going to pass down to 4 is going to be n minus 1 minus 3, which is just n minus 4. And again, same thing for this side. We're going to pass down n minus 4 because we've already seen 1 and 3 for both these paths. And if the path from 4 onwards or 5 onwards sums up to at least n minus 4, then back up to 3, we're going to have a value that sum up to at least n minus 1, and back up to 1, then our path has to at least sum up to at least n. So here we have a sum, and we have list comprehension. So we want to iterate for c in t.children. And we're just going to call a big path on the subtree c, and the value we're going to pass in is going to be n minus t dot label. So moving on to problem 3b, here we're going to use big theta to represent the number of paths in a tree with n nodes. So in which that every non-leaf node has at least 2 children. All right, so the very first thing you can think of when you're looking about trees and recursion is that, oh, because each one has at least 2n branches, there's going to be 2n. But you're going to be careful about this because you actually want to analyze what it means to have the number of paths and how is that going to increase as we increase n, right? So we use the same tree from before. We look at 1. This is one new node, and so we're going to have one path, right? And then we're going to add a new node 2 on there, and we're going to have 1, 2, 2. That's going to be another new path. We add 3 on here. It's going to be 1, 2, 3. So another, again, new path. And what if I add 4 here? Then it's going to be, what happens was at 1, 3, and 4. And we get 1, 3, and 5. Notice that each time I'm adding a node, I am increasing the number of paths. So I'm increasing the number of paths by at most 1, right? Paths by at most 1. Because when I add 4 here, this path is actually it's gone. Because 1 and 3 is no longer a path. So that was adding 0 paths. Whereas when I added 5, 1, 3, 4 was still one path, but I'm adding 1, 3, 5, which is only one new path. So this means that as we increase n, the number of paths is going to increase by at most n, because each additional new node can only increase by at most one path. So since we're using theta, this is going to be theta of n. In our path, this is a more generalized version of big path. Right now, we're going to have a number of paths such that this f of reduce g, p, and s is true. So reduce, what it actually does is that given some function, some iterable, and some starting value, it's going to go through each value of the iterable, apply function and s to the first value, accumulates it to total, and then goes to the next value of the iterable, and then applies function and the total, and keep accumulating until we reach the end. So if we were to add some iterable, let's say 1, 2, 3, and a starting value of like 5, it's gonna go 5 and 1. This adds together to be 6. It's gonna look at the next value 2, adds together to be 8, and then 3. We apply add, we're gonna get 11. Notice that this is like an upside down tree. That means that we do not have to use reduce in this function, because the way reduce works is that it's a bottom-up tree, right? It's making a bottom-up tree. So let's begin by looking at this example. T of even power of 2, right? So at the first value of 1, what it does is our starting value is 2. We're going to take the power of 1 and 2, and they're going to pass it down to both left and right. On the left side, this value is passed down, so this becomes our total of the accumulator. And so we're going to do power of this value, and then 2 here. And in this case, we want to keep going, so the value we're going to pass down here is going to be power of 1, 2 from the top, and 3, right? And then we're going to pass this down to both 4 and 5. And at the bottom, we want to make sure that calling f on the value returns true. So here we're going to call f, which is going to be even, right? So this is going to give us an even value, right? 2 to the power of 1 is 2, to the power of 2 is going to be 4. That's even. Whereas on these sides, 4 and 5, so 4, the value here is going to be even as well, whereas at 5 is not going to be even. So that means that when we're reaching a leaf, we want to check whether combining together s and the label is going to return true when passed into our filter function. So first, to reduce the leaf value and s together, what you want to do is just call g, which is the accumulator function that we have of s, and t dot label, right? So this is going to return some value, and now we're going to pass it into f, and that's going to return true or false. And if it's true, it's going to go to 1 and return 1. If not, it's going to return 0. So the number of paths at that leaf is going to be determined by this, the result of this function here. Now, what about the recursive case, right? Again, we're doing a sum over certain values. So it's going to be looking at the subtrees, right? So for s and t dot children, we're going to make the recursive call to all path, where now the tree is going to be a smaller version of s. Is the function f going to change? Well, no, because the function f is only going to be applied at the very bottom of our tree here. So f is going to stay the same. So same thing for g, because g is the same function we're accumulating, right? So in reduce here, add is being added in both, in every single step, right? But what about the value s we're going to be passing on, right? So you can think of s as both the starting value and the total value we're accumulating. So after we have moved on from 1, and then applying g on 2 and 1, the new value is going to be power of 1, 2. So this value is passed down to the recursive call of this subtree. So power is g here, and we're going to pass in the value that's passed down, or the starting value, whatever, depending on which depth of the tree we're at. And the other value is just going to be t dot label. So we're going to accumulate, this is one accumulate action. We're going to pass down to the next portion of the tree, and then keep going until we reach a leaf. And at that point, we're going to call f to make sure that it's true to return 1. Now, since all path is a generalized version of big path, what we could do is we can use all path to write big path, right? So in big path, again, we want the number of paths in T such that the sum is larger than or equal to n. So our filter function must check whether this value that we're passing in x has to be greater than or equal to n, right? So at the bottom, we're going to make sure that the value we're having here has to be at most n. Well, what about the starting value? Well, in big path, when we have not looked at any values of the tree yet, the starting value is 0 because there's no path. Then the sum of those values is 0 because we have not seen a tree yet. Right, so s here is going to be some value 0, and here, since we want to define a function, but we don't have a one line, we're going to use a lambda function, which takes in one argument, and it's just going to compare whether x is greater than or equal to n, right? So at the bottom of our tree, so 1, 2, 3, 4, 5, at the bottom of our tree, it's just going to compare, it's going to take a g, some value g, takes 1 here and 2, and then checks whether the result of this is greater than or equal to n. So now we're going to think about what is this g, right? So here the g would be 1 and 3. Right, here the g would be g of 1, 3, and 4, g of 1, 3, and 5. Right. In big path, we want the sum to be larger than or equal to n. So to sum things up in this way, g must be adding 1 and 3 together, and then add 4. Right, so 1 plus 3 plus 5 to obtain the sum. So at each step, we're going to be adding a new element onto our current sum, into our current s. So g is just going to be the function add. And this is how you would write big path using all path. For this question, cucumber, the main thing is that we want to really truly understand the question and then think about how we want to implement the class round, right? And think about what play round is doing. So here in this game, we're given 4 players, which is numbers 0, 1, 2, and 3. In each round when we play, we're going to be passing in who is playing and whose card, right? And this is obtained from iterating over this list of tuples that represent the player and the card they're playing in that specific round. So at the end of the round, some player is going to be taking control of the game, and that player's card is at least as high or higher than the highest card played so far. Basically, their card is the max or tied for the max. But since they were the last player to play that value, they have control. And the winner is just that last player who is in control. Right. So first, let's think about what we're doing here. R is round.starter. So starter is the starting player for that round. So in this case, in the init, starter gets set as both self.player and self.starter. And self.highest gets set to -1. We're going to assume that for each player, they're not going to play any single card value that's less than 0. So we use -1 to denote the start of a round. Right. Now, think about this, right? It's at the result. What's going to happen is that we're always going to return round.winners, and every time we're playing a round, our dot winners are going to get appended by the next player who's won, right? So our dot winners is just a list of sequences that contains the players who have won in some round that we've played. So here, let's think about play around with the first doc test. We're looking at 3 is a starter. So the first tuple that we pass in is 3 and 4. That means player 3 is playing, which is fine because that's what we want. And its value is going to be 4. Next is going to be 0. So remember that we go 3, 0, 1, 2, 3. So the next player after 3 is going to be 0. Here, 0 plays 8. 8 is larger than 4, so 0 is now the one in control. But we go again because in each round, every single player gets to play at one card. Right? So now it's 1's turn. 1 plays the same value as 0, but since 1 played the card after 0, 1 is the one in control. And 2's 5 is going to be smaller, so we're going to append 1 to round.winners and return round.winners. Right? In the next case, our starting player is 1. We're going to play our dot play with who as 3 and card as 5, but remember that the starting player is 1, so 3 can't be playing the first card. So we have this error statement that's returned. Next one is 1. We play 1. The current highest is 4, and then we play 2, which is fine. 2 comes after 1. The value is 5, so 2 is in control. And then onward to 0. 0 does not come after player 2, so we have an error again. And so this value doesn't even matter because 0 should not be playing. And we move on to 3. 3 comes after 2, which is fine. So we see that 7 is the highest number, so 3 is in control. And then finally, at 0, we play 6. It's not high enough, so we're going to append 3 to our round.winners. And so we're going to return round.winners. So we see a 3 is reflected here, and the 1 has won earlier. Moving on to the final doc test, we see that 3 starts, so we have 3 and 7. 7 is the highest value, 3 is in control. We move on to 2. This is an error because 2 can't come after 3. We have this error message, it's not your turn. And then we can move on to 0. Right, so 3, 0, which is fine. 9 is the current highest, so 0 is the one in control, but 1 never got to play. So since 1 never got to play, the round ends, and no one gets added to round.winners. So let's move on to the code. Right. So the sequence of players is from 0, 1, 2, 3, and then back to 0, right? So we see that we have a play function and a complete function, right? So what about why do we want to use complete? Why do we want to define a method here? It means that somewhere in play, we're going to use complete twice, right? So before we even fill out complete, just assume that complete means that checks that it returns true if round is complete. We assume that self.control is an instance variable of the player that's in control. And so in order when we're gonna append the person who's won to winners, it must mean that complete is the round is complete. So all we have to do is call self.complete here. And remember that since you see that we have player 1 in this doc test saying that this round is over, that means that we play so we start at 1, right? So 1 plays, 2 plays, 3 plays, 0 plays, and we're trying to play 1 again. So in this case, the round is already over, so there's no point in 1 playing a card. So this means that for this assert statement to be printed, the round must be over. So again, we have self.complete. Right. Now moving on to the second statement, it says that it's not your turn, player, whoever is playing. Remember that who is going to be the one that is going to be playing for that card. So we're going to use self.player to denote the player to play a card, because we can't use self.starter because that denotes whether who started the round. So here, if who is not equal to self.player, we're going to have an insert statement to say that who should not be playing. Right. So now we're going to move on to the actual code. We see that we're going to set self.player as something. So here in self.player, we're going to set this to the next player to play because we can't set it in anywhere else in our code. So here we're going to be updating to next player. So self.player is going to be at 1, but we only have 4 players in this case. Since we have 4 players, we can't go from 0, 1, 2, 3, and then 4. We have to mod it back by 4. But since we in OOP using abstraction, we actually want to use the self.players. So we're going to mod it by self.players. And this means that I can change this value here to like 5 or 10, and they can just change the number of players that can be playing the game. Right. So now in card is greater than self.highest, this is where we're going to update the person in control, and we also want to update self.highest, which keeps track of the highest card. So self.control gets updated to some value, which is going to be self, which is going to be who, because who is the current player that is playing. And then self.highest will get updated to card. Right. So we want self.control in here because we're appending self.control, and this instance variable does not appear anywhere else because it's not set until we go through a round. And since no player can play a card less than 1, the first call to play will always update self.control to who. Now moving on to complete. In order for a round to be complete, we have to come back to the player who started the round. So if we started at 2, we have to go from 2, 1, 3, and back to 2. So that means that self.player has to equal to self.starter. And this is also another reason why this update has to occur before we check the self.complete. But what if, but this does not know whether you finished the round or you're just starting, because when you're just starting your round, we're going to hit this check, and self.player is equal to self.starter in this case, because self.starter gets initialized as starter. So what we also want to check is that we want to make sure self.highest is not -1, because -1 is what denotes whether we are starting a round or not. Right? And here is the OOP solution. We see that we're making use of abstraction and not repeating code.
So this is 5A. This is the implement the group method, which takes a one argument function and a list. It returns a list of groups. Basically, if they're equal to f of x, they appear in the same order that they appeared in S. So let's look at the doc test. I think the first thing you want to do in this question is read the doc test. 5 is 3, 4, 5, 2, 1. So we pass in a lambda. That's going to check basically if the number is even or not. So this returned 1, right? Because 3 mod 2 is 1. This returned 1, this returns 0, this returns 1, this returns 0, and this returns 1 when we apply our lambda to it. So we're going to group all the ones together, all the numbers that return the same value, 1, together, and then we're going to return all the values that return the same number, 0. So 3, 5, and 1 get together, and 4 and 2 get together. And note that 3 comes first because it appears first in S. Same goes here. We apply x mod 3. So 3 mod 3 is 0. That's why it's by itself. 4 mod 3 is 1. 5 mod 3 is 2, and 2 mod 3 is 2 as well, so the 5 and 2 get together, and the 4 and 1 get together. Okay, so we start with an empty list for B and map. So sometimes we want to understand what the code they're giving us is doing. So map is going to apply our F to our S. So let's actually run through what map hypothetically should return. So map should return, if map F of S, map, remember, is going to return a new list that applies F to every element of S. So let's look through this example right here. It's going to apply our x mod 2. So we should get a 1. Actually, it's going to be this right here, is what I was talking about. We're going to apply our F. We're going to get 1, 0, 1, 0, 1. That's going to be this right here. So what does that mean? So for B and map. So we're going to be looping through every value in B. So what do you think we should do? We know we have A dot append B. So what could A somehow be doing? So A is going to be adding some values here. So do we want to add every value to A? That doesn't seem right. Why would we do that? So we need to check something. So it seems like we're going to have to somehow group our 1s together and group our 0s together. So we actually have to keep track of how many unique values there are in our map list. Like, for example, this example, it could be 1 or 0, 1, or 2. And we need to keep track of, does 0 appear, does 1 appear, and does 2 appear? So we actually want to say if B not in A, then we add it to A. So now, sort of at the end of our for loop, the end of our code, our A should have something like 1 and 0. Because the first time B is going to be 1. It's not in A already, so we're going to add 1. Then we're going to loop to the next B, which is 0. It's not in A, so we'll add 0. Then 1 is in A, then 0 is in A, then 1 is in A. Does that make sense why we need to keep track of our 1s and 0s, sort of the unique values? Okay, so then we need to return some sort of bracket for B and A. So B is going to be either 1 or 0 in our example, and we need to somehow group all 3, 5, and 1 together. So how can we get 3, 5, and 1? Well, we're going to have to loop through S again. So this is going to be another list comprehension, x for x in S, and then we'll have some condition. Does that make sense? So we can somehow get our 3, 5, and 1 by looping through S again. So what do we have to check? So we have to check if our f of x, so applying our function f to our value, actually returns b. Because if it does return b, for example, it's a 1, then we want to add the 3 to our bracket. If it's a 5, we want to add a 3 to our bracket, and yeah. So does this make sense why our final return value is going to actually have brackets, inside brackets? Because our value for our list, for this list comprehension, is a list, and we're actually doing another list comprehension inside of that. So that is the solution for 5a. All right, so let's move on to part B. So implement a group link, which takes argument f. It returns a linked list of groups. Same elements as group, f, yeah. Return a linked list of groups that contain all x with equal f. So again, look at the doc test. 5 equals link 3, 4, 5, 2, 1. That looks like the same doc test as above. Group link lambda, we take out we group together the odd ones and the even ones. So yeah, this is exactly the same as part A, where we group 3, 5, and 1 together. Then we group, 4 and 2 together, but except now we have a link. So to remember what linked lists are, remember they have a first, which could be a link, and a rest, which has to be either a link or empty link, which is actually an empty tuple. Okay, so if s is link.empty, return s. So this looks like that's a base case. We'll be doing some recursion, and actually we can see that right here. A equals filter link lambda x. So filter link is actually found on the last page of the final, but it's very similar to filter for lists and stuff. So we have filter link with lambda, it takes in an x, and then x mod 2 or something, and then we pass in link 1, then link 2. It'll get rid of what does it say? Return a link with the elements of s for which f returns a true value. So it'll get rid of this will output link 2 because this is the only value. This is the only link where the value returns true for our filter. So filter link lambda x, filter link, so b filter link lambda x as well. Notice how they use an a and a b. So it seems like a should be, and notice that our return link actually has a as the first element. So I think our a should actually return, for our first doc test, link 3, link 5, and link 1. And then we'll recursively group link for b, which should have everything except 3, 5, and 1. So we're probably going to have to filter our s in both of our cases. But then how can we actually filter out the 3, 5, and 1? So let's look at it. So we want all the values that actually return the same value for f. We want to find all the values where that have the same value as our first value. So this would be 3, 5, and 1. So if we look at our first value, f called on 3 is actually going to return 1. And we want to look for all the values in our link that have 1 here. So how can we do that? Well, lambda x, we can actually call f on x. And we actually want to make sure that this is double equal to f called on s dot first. So the very first time around, we're going to be calling it on 3. So f of 3 is going to return 1. And so then now we will look at now we will apply f to every element x in our s, making sure that if it is equal to f of 3, which is 1, then we'll keep it in our final link. So what does that mean for b? Well, that means that we want all the ones that are not equal to s dot first. Yeah. And it might seem a little confusing that aren't we looping through s as we are looking at through x's, so won't s here change? Well, it actually knows that this s is pointing to this s because we defined it in our lambda. Yeah, it's not the best explanation, but hopefully this makes sense. All right, so let's move on to 5c. The multigrouping by function f of a list is formed by following the iterative process. So first we group all the elements that yield equal values, and then we keep applying f onto those grouped values until until everything's in a single group. So let's look at their example. So for example, we have a function x. It takes the max of the parameter minus 3 with 0, and our list is 2, 4, 3, 4, 2. So the first iteration, or the 0th iteration rather, the values are grouped purely by their value, and that's really important. The 2's are grouped together just because they're equal to 2. We don't even apply f, so there's no f at all. No f. Then the first iteration, we apply f once to each element. So f of 2 is equal to f of 3, because 2 minus 3, the max of -1 and 0 is 0, and the max of 0 and 0 is 0. So we group the 2's and the 3's together. And then the 4's still have a max of 1, because 4 minus 3 is 1. The second iteration, now we apply it twice. Does that make sense? So we actually need to keep track of the previous value, f of 2, and apply that again. So for example, our f of 2 was 0, so then we'll actually do 0, -3, and the max is 0. F of 4 before was 1, but then now the max of 1 minus 3 and 0 is still 0. So now everything is grouped into one big group. So let's take a look at, let's scroll down, the doc test. So multi-group lambda max x minus 3, 0, 2, 4, 3, 2. That's the exact example we ran through. So this is going to be the final list. Notice that, yeah, so this is our final list. And then we notice how if we only have one element in our list, we just return it. That's important. And if we have two elements that are the same, we just group them together. And then we actually, and so for example, this one is going to be looking at it's going to get rid of the ones place. So it's going to group first the 12s together. Well, first it'll put all the numbers in their respective lists. Then it'll group the 12s together. And then it'll group the 14s together. And then it'll actually just group them all into one, because once you apply the lambda again, it'll cut off 2 and they all have 1. So, you don't have to go through all the examples. So we're going to be using a helper function that takes an g and s. If len s equals 1, we'll do something else. We'll use our group function from part A. And I'll remind you what that is in a little bit. And return using lambda, etc. So a couple things we can notice. We're passing in s into our helper function. And if the len of s is equal to 1, for example, this doc test, what do we want to return? We only want to return s0, because, we just want to take out that value and return it. And they gave us in the doc test, and that'll work out later on. This is important. So the first time we call using, we're going to be passing in some lambda function, and we're going to be using that lambda to group our values. Well, remember what we were talking about before, the very first iteration, we don't even want to apply f. We just want to group purely based on our x. So our lambda is actually just going to be an identity function. That's what they're called when you just return yourself. So that'll be our identity function. Oh, not here, sorry. Right here. So now let's walk through. So for example, let's pass in our f. Let's walk through this doc test. Pass in our f as this lambda. We pass in our s as 2, 4, 3, 4, 2. So I'll write that 2, 4, 3, 4, 2. This goes into here. Our lambda is going to be identity. Our len is not 0, so we're going to group it. So what is our grouped value going to look like? It's actually going to look like, we're going to group it based on our g, which is just our identity matrix, our identity function. So 2, 2, 3, 4. Does that make sense? Because we did that in part A. And actually, if you didn't even get part A, you could still do this problem just by taking the leap of faith. So what do we want to do here? We want to call our using function again, but now we actually want to call f. So let's just think, okay, well, let's call f. Basically what's going to happen is going to call using again. Using is going to run through this code. It'll group it again by our g that we pass in here. So we're going to change it. So we think, okay, maybe we just want to apply f. So what if we were to sort it by applying f to each group? And remember that each group has the same values by definition, by how we grouped it. So we only need to apply it to x0, right? Because for each x, it'll loop through each element of our list, take the first element, which should be the same as all the rest of the elements because of, they should be grouped correctly already, and then apply f to it. Okay. So this might seem like a good solution, and that will work for our first iteration, right? Because our first iteration is just going to be applying f to each grouping, which is what we're doing. But our second iteration, it's not going to work, because notice how our second iteration uses f of 2. So how can we call f twice? We don't want to call f twice here because, for example, if we called f once already on our groupings and grouped it accordingly, so for example, we called our function again, we got something like this, something like that. We don't want to be calling f again on that. So what we instead need to do is actually call the previous g function, because the previous g function will actually give us the result of calling f that many times. Sorry, actually, we could have called f twice. My bad. That would have worked for our k2 iteration, but it wouldn't have worked for our k equals 3, because then you would have f of 3. Sorry, yeah. So to get around that, we're actually going to use g, which should already be calling f the right number of times. Does that make sense? So our solution is going to be s0 here, lambda f g x0, and then lambda x here. Whoops. Yeah, I think definitely let that sink in and actually try go through the doc test yourself and run through this code. And we'll actually do that for part D as well. All right, so let's run through 5D, which is basically running our function and counting how many brackets they're going to be. So remember that our function is first going to group purely based on the values themselves. It's going to look something like this. And then it's now going to apply f once to it. So I'll make a little chart, I guess, applying it one time. We will get, for the 3, we'll get 3 mod 2 is not 0. So it's going to do 3 times 3 plus 1 is 10. So for the 3, and then for the 20, and for the 128. So we get 10, 2, or 20 run through this. 20 mod 2 is 10 equals, sorry, 20 mod 2 is equal to 0. So then we get 10 as well. Then 128 is an even number, so we will get 64. So notice how the 10s are already together. So that means we're going to group these two together because they have the same f1 value. I mean, they have the same value of f applied once. So I'll draw that over here, I guess. So 3, all in one bracket, 3 and 20 are now grouped together. And then 128 is grouped like that. All right, let's do it one more time. 2. So applying the function yet another time, we will get 5 here. We will get 5 here as well. Remember, now we only have to do it to one of them because we know they're the same. So we'll get 5 and we'll get 32. So none of them are, these are still the same, but 32 is still different. So it'll be something like, basically we're going to, I guess I'll wrap it all around in another one. 20 like that. And then there's yet another extra parenthesis or bracket around 128. That's our final list. And then we apply it one more time. So our third time, we get 5 is odd, 15, 16. So we get 16 here, and then we actually get 16 here. So what happens is we group it all into one big list, and then we actually we call our function yet another time, but we actually just get S0. So what's going to happen is we're going to wrap all this in another bracket, but then we're going to get the 0th element of that bracket, which is just this anyways. So our final result is going to be, our list is going to look like that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16.
All right, so looking at 6a, this problem asks us to evaluate the number of parentheses required to write a certain value in standard scheme notation. So what that means is we essentially want to go across our sequence and count the number of times parentheses shows up. So if you look at the doc test, when you pass in parens 3, it's going to evaluate to 0 because there's no parentheses in this. Whereas if you pass in parens list of 3 of 3, list of 3 of 3 is going to evaluate to 3, 3, and then evaluate to 2 because there's 2 parentheses. If you pass in parens of 3.3, it's going to evaluate to 2. And similarly, in this one, there's 2 parentheses total because it essentially simplifies first to 3, 3. For this test, there's 4. And this one, there's also 4. And for this last one, it looks like there's 8. So thinking about this problem, what I would do first is I would essentially jot down some notes. The first thing you have to notice is that there can only be an even number of parentheses. There will never be some odd number because every opening parentheses also has to have a closing parentheses. So that's an important thing to note where our value is going to be even. Okay. So, oops, let me just erase that. Is going to be even. The next thing that we want to note is that we somehow want to accumulate these values, right? And so looking at our skeleton code structure, what they give us is that they're defining some helper function inside. And what this helper function does is it's named f, and it takes in some s that we pass in from parens s, and then has a t. So our next step is identifying what t is. And we know that we're going to accumulate some value, right? We have to accumulate some parentheses. So we can assume that t will act as some count that we can accumulate. Okay, so the next step is essentially understanding that we're going to iterate across our list, right? If we think of these scheme sequences as some like linked list, right? We want to iterate across our entire sequence. And essentially, we can count on lists being inside the car of each respective node. So what that means is essentially we can just check the car of some list to see if there's more parentheses inside, if there's lists within lists, or if there's parentheses within parentheses. So we want to iterate across our entire list and then just check the car for more parentheses inside each section. So yeah, at the end, we know that when we're done, we could just return our t value. So that is one base case that we could keep in mind to identify later. So let's work with our skeleton code right now. What we see is they define some parens s, but also they have a helper function in here. So they're defining the parens s, which returns the call to some helper function named f. And now we know that t is going to correspond to a value that we want to accumulate. And so it can't be a Boolean, right? It can't be a false or a true. And so we can go ahead and just cross those out right off the bat. The second thing that we notice is that it starts at 0 or 2. We know that t has to start at some value, but we don't know what it should start at yet. So let's just leave that blank for now. We can come back and revisit that later. Inside of this helper body, we're given some condition, and these conditions correspond to a pair, a null check, and an else check. So in this pair, it looks like we're trying to add something to some value. Okay, and we know that we're accumulating our t value. And so it's safe to say that this might be some point of interest where we want to keep our t and accumulate it using some car encoder, like I said earlier, where we're going to iterate through this entire sequence and then count the number of times each parentheses occurs in the car of each subsequence. So right off the bat, we know that we can essentially eliminate some values, like 1, because we know that there's never going to be an instance where we have like 1 open parentheses and no closing parentheses. So we can iterate some strange odd values. And if t1, 0, we know that t will always be a true value. And so essentially what this does is return 1 always. So we can get rid of that too. Some other things we can also get rid of are these true and false booleans. So let's eliminate this. And okay, from here, we know that we're going to go into the null case as well. So let's work on the null case. Jumping around a bit, but in the null case, we see that we can either return 0, 1, 2, or t. And we said here, when we reach the null, when we reach the end of a sequence, we want to return just t, what we've accumulated so far. So now we can cross out all these values and return our t. And this if t 1, 0 still doesn't make sense, so let's just cross that out. We know that if our sequence turns out to not be neither a pair nor empty, then we're just gonna return 0. So this is the case for this stock test, parens 3. We're gonna pass in a 3, and then we're gonna see that, okay, it's not a pair and it's not empty, and so we're just gonna return 0 for this, and hence we have that. So the next thing I wanna consider is how do we get this recursive case going now? So what should we cross off for this part? Well, we know that when we have a pair, we have to iterate across the sequence, but then we could check the car of the sequence to see if there's any extra lists within lists. So if there are extra lists within lists in the car, we know that we're going to add on another set of parentheses at least. So we're gonna add another 2 parentheses to our count. So we're gonna keep our t, and then we're going to essentially add on 2 if we have car of s. So out of all of these car s options, we only have one, that's 2. And that's essentially this one. So let's cross out all the car s's that don't correspond to 2. So this one. And we know that because we're accumulating some t, we can also cross out this 2 as well. In our cutter, we're just iterating through the sequence as the recursive case calls it. And so we can get rid of all the cutters that don't correspond to 0, because when we iterate across, we're not accumulating any extra parentheses. And so we can get rid of this cutter, and we can get rid of this cutter. Okay. And so now the question is, what do we want to start with? We're really close to our answer. It seems like we've fleshed out most of the code. And so what we want to do now is walk through our base case and see if we could start at some value, whether it's 0 or 2. So we have this first case down, right? Now we want to go through this list 3, 3. This is some 3, 3. And so when we pass this into parens, what we're going to do is we could start it with 0 or we could start it with 2. So if we start it with 0, what is going to happen? Well, s is going to be 3, 3. T is going to be 0. And because it's a pair, we're going to increment t by some value. So we're going to increment t by the call, by the recursive call to the helper function when we pass in cutter of s and car of s, right? So we have to check the car of s. We know the car of s is just 3, and so this is eventually going to return 0 for us. And then the cutter of s is also just 3. It's not a list within here either. And so this is also going to return 0 for us. So in the end, we have t plus f cutter s 0 plus f car s 0. This is a 0. This is a 0. And we know that this is a 0. So that's not exactly right. I mean, we want to return 2. And so the most logical thing would be to start this t starting at 2. So we can erase this statement. And so this is our finished code. And let's just walk through a couple examples to see if we're on the right track. So let's look at these last few problems, these strange edge case ones. So we have empty parentheses and inside of another set of empty parentheses. So when we pass this value in, we're going to say, okay, s is going to be bound to this tuple within a tuple. And t is going to be bound to 2 because we set it as 2 when we call it. And so because this is a pair, we're going to say, car of S2 plus t, which is 2, plus cutter of S, 0. So the cutter of this is nothing. It's null. So what we're going to do is essentially just return t. And then the car here is going to be some value here. And we know that this is a set of parentheses, which should be 2. And so saying car 2 is correct. Because we know that t is 2 currently, and we're adding the car 2. And so that's just going to be 4. Okay. So walking through the last problem, what we can do is say we're going to pass in this sequence. And we know that t is going to be 2 plus the car of S, which is going to be this element in the beginning, right? Plus the cutter of S, which is going to be this longer element at the end. So it's going to be 3 like that. Okay, so we know our t is currently 2. And this one, if we pass in this subsequence into the helper method, it should return 2. So let's try it. So S is going to be this sequence. And then because it is a pair, what we can do is we can call f of car S on 2 and cutter of 0. So what we're going to do is we're going to make another call here. And the car of S is 3. And the cutter here is going to be some nil. And so this, we know that it has 2 parentheses. And this one, if we do the recursive leap of faith, it should be the first element is this list 3. And the next one is some nil. Whereas this one evaluates to some 3, nil. But that's 2 here and 2 on the outside. So it's 2, 2, and 2, and 2. So that is 8 here. So it corresponds to our doc test. So we know that the things we crossed out is correct. So moving on to part B, we want to write a quote expression that evaluates to some scheme list 1, list 2, 3, that has as many parentheses as possible in the expression. So a well-formed answer is quote 1, 2, 3, but this isn't maximizing the amount of parentheses we can have, right? So in order to essentially take advantage of maximizing our parentheses count, we want to use the dot notation next to the parentheses. Because we know that this still forms a well-formed list, it's just more verbose. And so looking at this problem, we have parentheses out here for the quote. And our first element in this list that we're trying to form is a 1. And because we're taking advantage of the dot notation, we're going to say dot. And our next set of items is going to be in this parentheses. Our next set of items is going to be 2 and 3, but the 2 is in a list itself. So we know that because it's in a list itself, we have to set another set of parentheses here for the 2. We're going to do another dot notation. And because it's a well-formed list, it has to be nil. And so we'll add a nil here. And so we have our 2 list here, and now we want to add our 3 at the end. So we're going to take another dot, add a 3 here, and finish it off with the dot in the inside here as well. So it looks like we have 1, 2, 3, 4, 5, because this parentheses corresponds to this outer one here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in the end, we should have 14 parentheses total if we're maximizing the amount of parentheses that we could pass in. Okay, so for part C, we want to analyze how many total calls to scheme eval would be required to evaluate parens 3 in your scheme interpreter. All right, so let's count this piece by piece using what we have here. So when we pass in parens 3, we're gonna make a call here, eval here, and here. And then when we enter this body by calling the function, we know that it returns fst, so f, s, and 2. So we're gonna call this, and then we're gonna eval each individual token inside. And inside of this body, of this helper function, there's the condition, right? So we have a cond, and we have pair s, null s, and else 0. Okay, so the first thing that we want to evaluate in this helper body is cond. So we have cond, and we're going to evaluate each of these. And so we already have these 3 evaluations, but inside of each evaluation, because S is not a pair, it's 3, it's not a pair, so we're going to evaluate pair S, and then because this doesn't withhold, we're going to go to the next condition, which is null and S. So we're going to evaluate null and S, and because 3 is not null, we're going to go to the else condition, which is just 0. So in total, we have, just count the number of underlines that we marked, and so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's our answer.
So here we are looking at a stream in scheme such that it returns the elements in the sequence that skips all the Fibonacci numbers, right? Basically all the non-Fibonacci numbers, that is what we want. We see that no fib is defined as calling P with 3, 5, and 4. So that's a hint. So we're going to start off as previous is going to be 3, current is going to be 5, and n as 4. So here's a sequence of non-Fibonacci numbers. So obviously we want 4 because it's not a Fibonacci number. And then we're going to move on, right? So by moving on, we want to jump to 6. But how do we know to skip 5, right? So when n becomes 5, we see that n matches one of these, 5 matches one of these values. And so we're going to skip 5, and we can move on to 6. But while moving on to 6, we don't know the next Fibonacci number to skip. So what's going to happen is that we're going to calculate the Fibonacci number along and pass it on as pref and cur. So here, previous gets turned to 5, and current gets added to 8. Right, so 6, we're going to keep it. So it's a stream. We have 4. We don't know, so we have a question mark to denote a stream. Here it's going to be 6, right? So 6 moves on to 7. Again, 7's not any of these values. And we're going to keep going. We're going to add it on. And then we're going to look at 8. 8 is same as current, so then we're going to skip it and move to 9. And at the same time, we're going to change this to 8 and change this to 13 and keep going. Notice that we never had to use previous, we just have to use current. So in an if case is that if current is the same as n, then we want to skip n. So what we want to do is recursively call p. We're going to skip n, so we're going to skip n to n plus 1. But at the same time, we also want to calculate the next Fibonacci number. So here we pass current into the next previous, and the next Fibonacci number gets calculated as previous plus current. Right. But if it's not equal, then we want n, right? We want to add n into our stream. So we're going to use con stream, passing in n. And the rest of the case is going to be a recursive call to p, because p denotes the stream such that our previous is going to be the same previous. We have the same current because n is still within the range of current. And the next value we're going to be checking is going to be n plus 1. And just close all parentheses. In the SQL question, we're going to make use of recursive select. So what a Hamming number is that it contains all positive integers with no prime factors other than 2, 3, or 5. So if we start off as 1, then multiplying 1 by 2, 3, or 5 gives us non-prime numbers that except those that are multiples of 3, 2, 3, and 5. Now, after looking at 1, we can look at 2 and multiply this number by 2, 3, and 5 and keep going. So this gives us to the recursive select because after we've computed some elements, we can use those elements to compute the next numbers in our Hamming sequence, right? So we see that T contains a table 2, 3, and 5 as K. So here table T has column K with 2, 3, and 5. And in our Ham N, this is where the recursive select comes in. So what should be the base number in the Hamming number? So we're looking at the sequence. We start off as 1, right? So you might think that we can just go, select all from T. But if we do this, even though we have 2, 3, and 5, we're not going to have 1. So we cannot select from T. We're going to have to select 1 as N. Remember that we have to give it a column name because 1 isn't the value. If we're selecting all from T, it will just use K as the column name. Right. We're going to select 1 as, since this is actually with local table, we don't have to denote the column name because it's denoted here already. Right. So after we have 1, we want to select from Ham again, but also T because T contains all the prime factors that we want, right? 2, 3, and 5. And what we want to do is that to get 2, I'm going to multiply 1 by 2 to get 2, 1 by 3 to get 3, 1 by 5 to get 5. So we've seen 1 already. Next time we want to compute some other element, we're going to take 2, multiply 2 by each of these values in K. So we're going to get 4, 6, and 10. Let's go this way and then that way. So we're going to get 10, right, somewhere down there. And 2 has been used. Then we look at 3. 3 multiplied by 2 is 6. It's already here. 3 by 3 is 9. 3 by 5 is 15, right? And then we're going to look at 4. 4 is going to see 8. 4, 3 is going to see 12. And 4, 5 is going to see 20. And this is going to fill in the sequence like that. So what we want, the Hamming number that we want is just going to be what we are at right now in Ham, multiplied by every value in K, because when we join, every value in Ham, every row gets matched up with every row in T, right? And we want it so that the Hamming number is less than 100 and increasing order. So the increasing order part is already done for you in this final select statement. We're going to order by N. So in this where, all we have to do is make sure that it's less than 100. So in this row, the Hamming number that we're looking at is N times K, not N. N is the previous Hamming number that we're using to compute the Hamming number in this row. So the where here is going to be the new Hamming number must be less than 100. So in the final question of this final, we want to select all positive integers such that it has at least 3 proper multiples that are less than or equal to x. All right, so let's not worry about 3 and let's not worry about x. Let's just see what a proper multiple is. So what it is that it has some value n such that it's larger than n and that n evenly divides m. So we're going to make use of mod here, right? And this has to be equal to 0. So we need both m and n, right? And that means we have to make use of 2 tables in order for us to have a join. The only current table that we have right now is actually a local table ints. All it is select 1 from and up to x. So we're going to 1 up to 20. So ints contains 1, 2, 3, 4, all the way until 19. Right? Now, the other thing that we're looking at is that since we need 2 columns, 2 values in the same row, int only has 1, right? So we're going to make use of joining, and by joining, we're going to join ints with ints again. This way, we're gonna get this join is gonna give us tables such as like 1 and 1, 1 and 2, 1 and 3, like, and then 2, 1, 2, 2. Oops, sorry, 2, 2, and then all the way down until 19 and 19. Right. That means that in each of these rows, one of these could be m. So let's say this is m, and one of these could be n. And we just make and we can just keep the rows such that n evenly divides into m. So the table we want to select from is ints as m, and also ints as n. Hold on. Let's use a and b because we have n here already, and we just want to select b's n. We're gonna treat b as the table as the ints that represent n, and a as the ints that represent m. And so we want b dot n such that we know that m has to be greater than n. So a n must be greater than n, and also b's n, right? So a's n has to be greater than b's n, and we need to enforce the rule that it's evenly divisible. So a dot n mod b dot n is equal to 0. Right. So does this takes care of the case that is less than or equal to x? Well, it does, because here int is created such that n is less than or equal to x. 20 never appears anywhere here, right? So all positive integers that's in the ints table are all values as less than or equal to x. So we don't have to worry about x in our select statement. So the other thing is that we want to make sure that we have at least three proper multiples. We see that the final result contains the integer and the proper multiple that we have. So something that can count the number of rows is count star. Right. So, but count star counts everything, right? What we want to do is we're going to group by b dot n. So here, let's look at 3 has 5 proper multiples. So what's going to happen is that we're going to see 3 with 6, 3 with 9, 3 with 12, 3 with 15, and 3 of 18. All of these is going to satisfy this where condition, and we're going to group them together. So here, we're going to group 3 by themselves, and here we could have something like 4 with something, 4 something as well. So each integer is going to get grouped by together. Count star is now going to count for each integer group. It's going to count the number of rows, right? So here for the integer 3 group, it has 5 rows, so count star is going to give us 5, right? So we only want to keep the groups such that it has at least three proper multiples. So our count must be greater than or equal to 3. Right? And it's only going to go through these groups, and it's going to keep the elements such that the count of the groups is going to be greater than or equal to 3. And since the output is a count, that's all we need.